So in the previous lecture, we have discussed that if f is continuous, if and only if the inverse image of open set is open set. Also, we have discussed that if f is continuous, if and only if the inverse image of closed set is closed. Also, we have discussed that if f is continuous, which is a function from x to y, and A is a closed set or open set, if it is continuous function, then it will not implies that f of A is open. Also, we have discussed that if f is continuous and f is 1, 1 and on 2, that means there is a existence of inverses there, but it will not implies that the inverse is continuous. Or I can say this map, if f is continuous map, it will not preserve the open set there, or it will not preserve the closed set. Preserve means if A is open, it does not imply that f of A is open. If A is closed, it does not imply that f of A is closed. Now, to regard to this, we will have another definition to come out with this situation, or to fulfill that it will preserves the openness from under the continuous map. We will have a next definition. It is known as a homeomorphic function. In each and every theory, whether you study about the algebra or you study about these metric spaces or any other theory or any other structure you can have, this homeomorphism is a structure that we are looking for, in which whatever the property of x we have, whether the same property will y we have. So that is kind of homeomorphism is there. So in the homeomorphism in this matrix spaces is defined like this. Let x1 and x2 be a matrix spaces and f be a 1, 1, 1, 1 function from x1 onto x2. That means f is a 1, 1 and onto function. The function f, it's called homeomorphism or homeomorphic function. It's called the homeomorphism. Between x1 and x2 if both f and f inverse are continuous. So if both the function, a function and its inverse, both of them are continuous, then we can say that x1, or then we can say that f is a homeomorphic or homeomorphism between the space x1 and x2. And this x1 and x2 are called homeomorphic spaces. So I can say that if I want to say that x1 and x2 are homeomorphic, then there will be some homeomorphism between x1 and x2. So this is the definition of homeomorphism or homeomorphic spaces. Now, with the help of this definition, we'll have next result, which gives you certain idea regarding this homeomorphic function. So let x1 and x2 are a metric spaces, be a metric spaces. Then prove the following. The first one, F is homeomorphism from x1 onto x2. Yeah, here we require that homeomorphism means that a function has to be 1, 1 and onto also. So that's why I've taken this homeomorphism. Then we can say that, or then F inverse is also is homeomorphism from x2 onto x1. So it says that if F is homeomorphism, F inverse is also homeomorphism. The second one, homeomorphism map open subset of x1 onto open subset of x2. That means A is open in x1 will implies f of A is open in x2. That means it maps open set to open set. The third one, it's regarding the closed set, that is homeomorphism maps a closed subset of x1 onto closed subset of x2. So this third statement says that if A is closed, implies that f of A is closed. That means it preserves the openness and closeness under the homomorphism. Let us try to prove these statements. So given that this F is homomorphism, that means F is 1, 1 and onto. And now I have to prove that F inverse is homomorphism. So what is the meaning of homeomorphism? That means that F is 1, 1 onto, F is continuous and its inverse is also continuous. So given that F is homeomorphism, this will implies F is 1, 1 onto continuous and F inverse is continuous. What I have to prove is F inverse is also homeomorphism. That means I need to prove that F inverse is continuous, which is already there. Then inverse of inverse is also continuous. So that I can write. And F inverse is, since F is 1, 1 and onto. F inverse is also 1 1 and onto. So we can say that we note that F inverse is 1 1 and onto. Also, F inverse is continuous. Now, what is the inverse of inverse? We know that it is F, but F is also continuous. So, also F inverse of inverse, that is F, is also continuous. Hence, this F inverse is 1 1 onto continuous, and its inverse is also continuous. Therefore, F inverse is homeomorphism. Which proves that the first statement. Now the next statement, that is the second one, it preserves the openness. That means if F is homeomorphism, then it will send to open set to open set. So let us consider what is our claim. Our claim is if G is open in X1 will implies F of G is open in X2. So I will start with, suppose that G is open in X1. Given that F is homomorphism, that means F inverse is continuous. Given that F is homeomorphism, therefore F inverse is continuous from X2 to X1. Since F inverse is continuous, inverse image of a continuous function is continuous. And this G is open in X1. So I'll pick up inverse. So G is already open in X1. So therefore what we can say is F inverse of inverse of inverse. F inverse of G is open in X2. Now what is F inverse of inverse? It is nothing but the F of G is open in X2. So which proves that if G is open, implies that F of G is also open under the homeomorphism. I may give the third one as your way, just you need to replace this open word with the close. I think so you are able to do that by yourself. That means in the next task we have to prove that the next is our claim is F is closed in X1 implies that F of F is a closed in X2. Means that this function F preserves the closeness. Again with the same argument as we have did it here. Suppose that F is closed in X1. Given that F is a homeomorphism, therefore F inverse is continuous from X2 to X1. That means inverse image of any subset of X1 will be, or closed subset of X1 will be closed in X2. So therefore F inverse of F is closed in X2, and therefore F of F is closed in x2. So which completes the proof that this homomorphism map preserves the closeness and it preserves the openness also. Now we have a next definition. That definition is called open map. So can somebody from you can guess what should be that definition regarding the open map? What should be the definition of open map? When I can say a map is open? A function f from x1 to x2 is said to be open map if f of g is open in x2 for every g open in x1. That means a map which send open set to open set, that is called the open map. Okay. In the similar manner, we have a next definition is a closed map. So when we can say a map is a closed map, same way we can define a function f from x1 to x2 is said to be a closed map if f of f is closed in x2 for every closed set in x1. That means it will map a closed set to a closed set. Now the question is, what will be the relation between homeomorphic map or homomorphism and this open map? So I have a two statement. The statement number one, f is homeomorphism. Another statement is f is open map. So which statement implies which one? Whether one is implies two or two is implies one. What is your answer? Yes, guys, I'm asking you. If f is homeomorphism and f is open, what we can say? One is implies two or two implies one. Let us given that f is 1, 1 and on 2. It is given. Then what we can say? See the first.
The one implies two.
Yeah, one implies two. We already proved in the previous statement, in which we have proved that f is homeomorphism. Then it preserves the openness. So it's exactly the same statement we have here. So this statement is true. This statement is not true. We have already given a counter example for that. Why? Because the openness, if f is open, we will not say that it is a continuous map. We cannot say that. So to do this second one, we have a next result, or to fulfill this if and only part, we can say that f is open plus continuous. then this 1 is double implies 2. So that is the next result we have. It says that let us consider this f is function from x1 to x2 be 1 1 and onto map. Then prove that f is homeomorphism if and only if f is continuous open map. So it is continuous plus open, then it will be homeomorphism. The one part is already we have proved actually in the previous lecture. That means if f is homeomorphism, then we know that f is continuous and it is open map. That we already proved in the previous statement, or we have proved that. So let us try to give the proof for that. That if f is homeomorphism, then it is open or converse, and converse also. So let us give the proof for this. So suppose that if f is homeomorphism, therefore we have proved, therefore f is continuous and f is open by previous result that I can write down here. Previous result means we have proved this statement that G is open implies f of G is open. That is exactly the definition of open set, open map. So that's why this is f is continuous and open, and so therefore f is open map. So it is f is continuous open map. So that proves that statement. Now conversely, suppose that f is continuous open map, we shall show that f inverse is homeomorphism. Sorry, f inverse nahi, f is homeomorphism. But it is equivalent to prove that f inverse is continuous, because what is the meaning of homeomorphism? It says that f is 1 1 and 1 2, which is already given. F is 1 1 and 1 2 is given, and f is continuous is also given. So it is sufficient to prove that f inverse is continuous. So it is sufficient to prove that f inverse is continuous. So how to prove that f inverse is continuous? So I have to prove that inverse image of, so it is a continuous map from x2 to x1. So I have to start with open set in x1. I have to prove that its inverse image will be open in x2. So let us start with that. So let G is open in x1. Now, since f is open, we can say that f of G is open in x2 because of f is open map. So that is the definition of open map. So therefore we can say that f inverse of G is open in x2. That is the inverse image of open set is open. So that proves that F inverse is continuous from x2 to x1. So hence F is homomorphism. So which proves that F is homomorphism if and only if it is a continuous open map. I'm giving you next problem or next exercise to you guys. That can somebody guess what will be that exercise?
F is homomorphism if and only if F is continuous closed map.
Yeah. So it is F is homomorphism if and only if F is continuous closed map. Here F is 1, 1 and 1, 2 is given to you. So you have to prove this statement. I am giving you this is as a homework. And try it by yourself. Now the next definition is about the isometry. What do you mean by iso? Iso means 1. Metry means a distance. So that means a distance is 1. Same distance. Iso means same. So when I can say the F, it's called isometry from x1 to x2 if, so I should not write if here. So if F is called the isometry from x1 to x2 if the distance is preserved from x1 and x2. That means whatever the distance between 2 points is here, the same distance of their images. That means a distance between x1 and x2 will be same as a distance. So this is the distance. I can say it is a metric which is on x1 is d1 and metric on x2 which is d2. Then this distance should be same for every pair of x1 and x2 in x1. So for every pair, if the distance is same, then it's called the isometry. Now the question is this isometry implies 1, 1? That means if F is isometry, can we say it is a 1, 1 map? This is the question. What is your thinking regarding this? 1, 1 map means we know that x is equal to y will implies f of x is equal to f of y. Then we can say that f is 1, 1. So here, if d is this, if x is equal to y, then this side is 0. If it is isometry, then that side is also 0. So we'll have x is equal to. So I can start with x is equal to y. Will implies the distance between x and y is 0 due to the a definition of a metric, and this will implies due to the definition of isometry, and so this is fx is equal to fy due to the definition of a metric. So therefore f is 1, 1. So that means what we have proved here it is that f is isometry will implies that f is 1, 1. Now the question is what should be the relation between this isometry and homeomorphism? Can I say that isometry map is homeomorphism? Definitely the onto-ness is not there, so I can add then. So isometry plus on 2. 1, 1 is already there. If isometry is there, 1, 1 is already there. So plus on 2. Can I say that it is homeomorphism?
Sir,
Yes.
sir, પેલામાં f of x is equal to f of y implies x plus y નહીં આવે?
X plus y?
Sorry,
Yeah.
x is equal to y.
X is equal to y. એનો મતલબ કે distance, the points are same. That means the distance between 2 points is 0.
સર 1 1 માટે આ તો આપણે ફંક્શનની ડેફિનેશન દીધી એવું ના કહેવાય.
Oh, yes, yes, yes. Oh, yes, yes. Undu, but same statement. Yes, you are right. So I'll start with f of xy is same. This is same, which implies that d2 of fx fy is equal to 0, which implies that fx is equal to fy, which implies that x is equal to y. Sorry, what I'm doing. This will implies that d1 of xy is 0, which will implies that x is equal to y. So therefore f is 1. Okay, now it's correct. This is due to the definition of a metric. This is due to the definition of isometry. And this is again definition of a metric. So if f is isometry plus on 2 is there, can we say that it is homeomorphism? So answer to that question is yes. We can say it is homeomorphism. So that is the next result. It states that if f is isometry from x1 to x2 onto x2, then prove that f is homeomorphism. So that is the next result. We can state that let f be an isometry from x1 comma d1 onto x2 comma d2, then prove that f is homeomorphism. From x1 to x2. What does it mean? That if two spaces are isometric, then two spaces are isometric onto isometrism is there, then it will be a homeomorphism. A converse is not true. Obviously, we can say that, because if the homeomorphism doesn't implies that the distance will be preserved. Okay. The converse example you can find out easily. So let us try to prove this statement. Since this given that f is isometry between x1 and x2, it is 1 1 and 1 2. So f inverse is defined. That we can write first. Since x1 and x2 are isometric metric spaces, f is one one, and given that f is on 2, therefore f inverse is exist. Now ultimately what we have to prove is f is homeomorphism. That means we have to prove that f and f inverse, both of them are continuous. So what is our claim? Is f is homeomorphism. So it is enough to prove that f and f inverse are continuous. F is homeomorphism. From x1 on to x2, it is enough to prove that f and f inverse are continuous. So claim 1, that is f is continuous. How to prove that f is continuous? So there are many ways to do this. Continuity is there. We are using the definition I have discussed any 7 of that equivalent statement you can use and to prove that f is continuous. I'm starting with this sequence definition or sequence condition statement. Xn converges to x in x1 comma d1 will prove that f of xn is converges to f of x. So since f is isometry, we have a d1 of xn comma x is equal to d2 of f of xn comma f of x. For every n and for every x we have this. This is the statement 1, which tells you that if xn converges to x, will implies the distance between xn and x is tending to 0. So due to the statement 1, the distance between f of xn and x is tending to 0. So which proves that this f is continuous. Now claim 2, that is f inverse is continuous. So for that, again, if I use this same technique, then let us consider this yn is converged to y in y2. Since f is 1, 1 and on 2, we can say that there exists a distinct points xn and y, xn and x. Since f is 1, 1 and on 2, there exist a distinct points. That means for each n, we'll have a distinct xn and x in x1 such that f of xn is equal to yn and f of x is equal to y because of onto-ness and one-one-ness. Therefore, xn is equal to f inverse of yn because they are distinct. We can write this, and x is equal to f inverse of y. So by isometry, what we can say is distance between xn and x is same as distance between f of xn and f of x, as f is isometry. That is our assumption. We have this. So this will implies that distance between f of x, f inverse of x, f inverse of yn. If I substitute the value of xn here, that is f inverse of yn, f inverse of y is equal to, this is a d1 distance, this is d2. So I should write that is also. That is f of f inverse of yn, and this is f of f inverse of y. So this will give you d2 of yn comma y. But this yn comma y is tending to 0 as n tends to infinity. That we have here assumed in the previous slide. We have assumed that this yn is tending to y. So that means distance between that two tending to 0. That means the distance between this f inverse is also tending to 0. So what we can say is, if yn converges to y, which implies in space x2 implies that f inverse of yn converges to f inverse of y as n tends to infinity in x1. So therefore f is inverse is continuous. So hence we can say that this isometry implies, if it is onto isometry is there, then it will imply homeomorphism. Okay, so that means f is homeomorphism. Now let us discuss some of the another results or examples related to this isomorphism, and then so let us see some of the example prove that the closed interval 0 1 and closed interval AB as a subset of R with absolute metric, or I can say usual metric, are homeomorphism. That means whether you can write down the closed interval 0 1 or any interval AB will be homeomorphic spaces. So if you can study regarding the open this closed interval, it is equivalent to study regarding any any closed interval is there. So if I want to prove that it is homeomorphism, I need to find out one map from this space to this space, which is 1 1 on 2 continuous, and its inverse is also continuous. So can somebody give me that function? So define a map f from closed interval 0 1 to AB as. So ultimately what is you need to find out, actually, suppose these are the 2 points you require. That means your 0 is mapped to A and your 1 is mapped to B. Okay, so that is the point you can have. The easiest map you can find out a straight line joining that 2 points. So suppose this is 0 and this is your point 0 comma A, another point is 1, so that is 1 is here. Then let's say the 1 comma B is here. This is the point, and you can have a straight line joining between these two. That is the function you can define. So what is the line joining these two? Can somebody define that function? Or can you find out the line joining between these 2 points? You know the formula is y minus A, that is y minus y0 is equal to m into x minus x0. M is the slope of this line. So this is the point. If you consider, then it is m will be b minus a upon 1 minus 0 into x minus 0. So the line you will have it is a plus b minus a into x. So that is the map I have to define. So define as f of x is equal to a plus b minus a into x. Now you can easily prove that, or I can give you an exercise that prove that this f is 1 1 and 1 2, and you can also prove that this f is continuous. That is, I am giving you as an homework to do. What will be the inverse of this function? Why this is continuous? Because it is a polynomial. So that is in one line you can just write down. But what will be the inverse of this function?
X minus A upon B minus A.
Yeah. So f inverse of, let's say, y, then it is y minus b upon b minus a is the inverse of this function. And that is also here x is belongs to x. This is my space x and this is my space y. So this is y is belongs to AB. Okay, so now I'm giving
Sir,
you an exercise.
sir, it will be Y minus A upon B minus A.
Yeah, y minus a upon b minus a. So you have to check this thing, that is f is 1 1 onto f is continuous and f inverse is continuous. Once you do that, you have a map, or you can say that this closed interval 0 1 is homeomorphic to closed interval AB. What does it mean? It means that whether you will study regarding the closed interval 0 1, it is equivalent to study a closed interval AB. Okay, so that you can able to prove that here. These are the another examples I can give you so that you can have certain idea. What does it mean of this homeomorphism? How powerful it is? So can you prove that open interval minus pi by 2 to pi by 2 is homeomorphic to the minus infinity to plus infinity? That means if you study regarding this open interval, that is equivalent to study a real line. So can you have a map which is 1 1 onto from this space to this space? Or I can say a question is prove that this interval and this real line are homeomorphic spaces. So ultimately I need a function from this space to this space. Another question I'm giving you that prove that open interval 0 1 and open interval 0 to infinity are homeomorphic. This will never be homeomorphic to each other. Close interval 0 open 1, because we have proved that if it is homeomorphism, then it is preserves the openness and it preserves the closeness. So due to that, this will never be true. So in many competitive exams, they are asking a question on this topic, that whether this map is preserving the openness, that means one side is open on the one side, whether its image will be open. So it is basically a checking regarding the homeomorphism between two spaces. Okay, so what will be the anyone have the map from this space to this space, which is 1 1 onto continuous?
Sir,
Just
fx is
this
equal to 10x.
tan inverse of x, not tan x.
Ha, 10x.
Tan x is from this to this. That means from R to this, tan x is. But tan inverse of x is from this to this. What about this? 0 to, which maps 0 to 0 and which maps 1 to infinity. So you know that log 1 is infinity, so the function is log x. That you can check. Okay. So I'm giving you one more exercise which is out of track from this, but I'm giving you that is also as an exercise, that f is continuous, then prove that, or if and only if the closure of A, which is a subset of whole closure. So that is, this is the statement, f is continuous from x to y. This is double implies f of A closure is subset of f of A whole bar for every subset A of x. This is there. So a continuous map is there. This is out of track. This is nothing is related to this homeomorphism and all, but you can prove this is by separate as a result. This is also I'm giving you as a homework to prove yourself. Okay, so I will stop here for today. If you have any question, you can ask.